Hi, this is Hari Krishna. You are watching High School TV by Hari. Look at the question. Use Euclid division lemma to show that square of any positive integer is of the form 3p plus 1. Proof. By using Euclid division lemma, we can represent a number a equals to bq plus r. Here r is remainder greater than or equals to 0 and less than b. B is a divisor. We have to prove square of any positive integer is of the form 3p or 3p plus 1. Let b equals to 3 because our proof also having the multiple of 3. This Euclid division lemma becomes a equals to b. In the place of b, 3 q plus r. Say it is equation number 1. Now case 1. When remainder r equals to 0. This is the equation when remainder 0 in this a equals to 3q plus remainder 0. That implies a equals to 3q. Asking question is show that square of any positive integer. Applying square on both sides. Yeah, that implies a square equals to 3q whole square. That implies a square equals to 3 into 3 into q square. Here a square equals to 3 into, here 3 is an integer, q is also integer, q is integer, q square nothing but that is also a integer. This integer multiplication, integer into integer we get integer only, 3 into this integer total part I am considering as p because proof is in terms of p there. So 3 into p, a equals 3 into p nothing but 3p, a square equals to 3p. First one proved, square of positive integer in terms of 3p. Case 2, when remainder 1, here remainder 0 first case, remainder 1 is second case. This equation 1 implies a equals to 3q plus remainder substitute 1. Applying square on both sides. This a square equals to 3q plus 1 whole square. Here 3q plus 1 whole square, it is in the form of a plus b whole square. That implies a square plus b square plus 2ab. Remember this formula. In the place of a, it is 3q. In the place of b, it is 1. This equation becomes a square equals to a plus b whole square. A square, it is 3q whole square plus 1 square plus 2 into a is 3q into b is 1. A square equals to, it is 3 into q square plus 1 square nothing but 1 plus 2, here 2 into 3q into 1 nothing but 2 into 3q only. That implies a square equals to, here what is the common in these 3 terms? From these 2 terms 3 is a common. Right outside the bracket, remaining here 3 taken out, remaining 3 q square plus from this 3 taken out, remaining 2 into q, it is 2q plus 1 separate the right as it is 3 into something That implies a square equals to 3 into, it is a q integer, 2 is also integer, 3 is also an integer. Integers plus integers, we get integer only. I'm considering this total in whole part integer as p. 3 into p, nothing but 3p plus 1 there, 1. A square equals 3p plus 1, it is second one. Second one proved. Case 3, one remainder r equals to 2. By the Euclid division lemma, remainder always less than divisor and greater than or equal 0. Here remainder always less than divisor b. Here b in the place of b, 3 there, less than 3 and greater than or equals to 0. R less than b, remainder less than 3 means we take up to r 2 only. Case 3 is r equals to 2. Then equation 1 implies this: a equals to 3 into q plus 2. In the place of r substituted 2. Applying square on both sides, it is a square equals to 3 a square equals to 3q plus 2 whole square. It is a in the form of a plus b whole square. It is a, it is b, a plus b whole square. Its expansion is 3q whole square, a square plus b square means 2 square plus 2 into a, 3q into b. B is 2. That implies a square equals to, this expansion is 3 into q square plus it is 2 square is 4 plus it is a multiplication 3q into 2 is 4. A square equals to, now here 4 should be right as sum of two numbers, 3 into q square as it is. 4 can be written as 3 plus 1, sum of two numbers, into 3q into 4. That implies a square equals to, from these three terms, here we have 4 terms. From 3 terms only we have common as 3, right outside the bracket. Remaining here 3q square plus here 3 taken out remaining 1 plus here 3 taken out remaining 4 into q, nothing but 4q, bracket close, plus 1 here 1. Similarly 3 into this total part is an integer like this, and this total integer I am considering as p, 3 into p plus 1. Second one, observe here when r equals 0 we got a square of this a is nothing but positive integer, square of positive integer, it is in the form 3p. And in the second case square of positive integer 3p plus 1. In the third case square of positive integer a square equals 3p plus 1. This like if we apply any square to the any positive integer, that will be in the form of either 3p or 3p plus 1. Hence proved. How to verify this 3p and 3p plus 1 are the square of a positive integer form? Let's see. Verification, I am taking square of positive integers 1 2 3 4 5 6 dash 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 1 square, its value is, that implies it is in the form 3 into 0. P is the integer, 3 into 0 plus 1. 0 plus 1 is 1. It is in the form of 3p plus 1. Next 2 square nothing but 4. It is 3 into 1. 3 ones are 3 plus 1 is 4. It is in the form of 3p plus 1. 3p plus 1. 3 square is 9. 3 into 3. 9 plus remainder nothing there. So 9. It is in the form of directly 3p. 3 into 3. 4 square is 16. It is in the form of 3 into 5. 3 5 is 15 plus 1 total 16. Nothing but it is in the form of 3p plus 1. P is nothing but a integer. 5 square is 25. That implies 3 8 is 24 plus 1 it is 25. Nothing but it is a 3p plus 1. 3p plus 1 form 6 square 36. Here 3 into 12. 12 3 is 36. No remainder. Directly it is in the form of 3p. This like we can apply square to the any positive integer. We get their form either 3p or 3p plus 1.